Okay, so we are moving to the next speaker. We are having Diego Fernández de la Pradilla from the Autonomous University of Madrid. So, Diego, when you want.
Okay. Hello, everyone. Thank you to all of the organizers for letting me present my work, and thank you all for staying for this talk. I hope you find it interesting. So we're gonna switch gears a little bit. We're not gonna discuss any more quantum information protocols directly. I'm gonna focus on open quantum systems in general. We've had already some talks where open quantum systems have been mentioned. But at the risk of sounding a bit repetitive, I'm going to make a small introduction of my own. So the first thing we have to consider is whenever you have an atom, quantum dot, whatever kind of system that you imagine, it's always coupled to its environment. And that means that it radiates energy, it decoheres, and all of these things that are not necessarily very good for quantum information technologies and so on. So in general, the theory of open quantum systems tries to find a way to describe the dynamics of this system, forgetting, in some sense, what happens to the environment. We don't keep track of the environmental degrees of freedom. We want to find a way to trace over those degrees of freedom and reach an equation that only cares and knows of the system density matrix, in such a way that the environmental effects are captured by the parameters of this equation. These equations are generally known as quantum master equations, and there are many to choose from, with different degrees of approximation, different degrees of mathematical accuracy, whatever. We're going to focus on the Bloch-Redfield equation and the Lindblad equation in this work that I'm going to show you. So let's present our main characters. The Lindblad master equation looks like this. I'm sure many of you are familiar or have used them. It's a very nice mathematical equation because it's rooted in a mathematical theorem, Lindblad's theorem, that tells you that it's the most general dynamical map that preserves the trace of the density matrix and preserves the positivity of it, which means, in short, that if you start with a physical density matrix, it will remain physical forever. It has a small drawback, which is the fact that Lindblad's theorem itself doesn't tell you what the parameters have to be. It gives you some constraints, but you don't know which values these parameters take. And this is when the Bloch-Redfield equation comes in handy, because although it looks a bit more complicated, it has some structure to it, but it looks more complicated than the Lindblad equation. It directly comes from a microscopic model of the environment. So if you manage to model it decently enough, these parameters, the capital lambdas and capital gammas, are things that depend on the environment directly. However, its pitfall is that it can give non-physical density matrices. It can give rise to negative probabilities and things like that. We don't want that. So basically, we have two equations. One is good on a mathematical basis. The other is good on a physical basis. Wouldn't it be nice if we could find a way to have a master equation that satisfies both things? And the common approach is to basically try to take the Bloch-Redfield equation and fit it into a Lindblad form by doing some manipulations and mathematical tricks. The most common one is the secular approximation, which basically you just take the Bloch-Redfield equation, you prune it, you cut some terms, and you get something that is guaranteed to be a Lindblad equation whose parameters are microscopically derived because they come from the Bloch-Redfield equation, right? However, secularization, although it's a very widespread procedure, it's not always perfect. Here I'm illustrating it with just one simple example. If you imagine that you have an atom inside a cavity and they interact with each other, and you would imagine that you have the atom initially excited, and then it undergoes coherent Rabi oscillations, and the excitation of the atom now becomes a photon, a cavity photon, and so on. And because the photon is leaky, you have that exponential decay, and the ground state of the whole system becomes populated. And you can see in the black line of the ground state, it is essentially becomes populated in steps. Whenever there is cavity photon, we have decay. When there is no cavity photon, we don't have decay. Well, if you try to describe this system with the Bloch-Redfield equation after a secular approximation, well, it misses completely that stepwise behavior. This is just one of the many examples that I could choose. It's a particularly simple one to explain and maybe more relevant to this community. But the take-home message is that we need something else in general. And this is where these guys came really clutch. They proposed a way to manipulate the Bloch-Redfield parameters to take geometric means of them in certain ways. And basically what they showed is that the equation you end up with is a Lindblad equation almost always. I mean, they claim that it was always because they didn't do a thorough analysis in some regards. But for relatively simple systems, it's a guarantee that it's a Lindblad equation. And it works for some reasons. If you want, I can delve more deeply. But again, it works. We used it in our previous project. It's a more complicated system than the ones they were considering. And that's when we found out that not everything was bright under the sun. There were some problems with their approach that came essentially from the geometric mean procedure that they applied. And now I'm going to explain to you what those problems are so that we are all on the same page. The first one is that the brown term there is basically the energy correction due to the environment. And it turns out that it can be a non-Hermitian, and that's not good. It can be non-Hermitian because basically you have to take the geometric mean of a positive and a negative number, or you may have to face that situation. And whenever that happens, it's non-Hermitian, and that's not good. The other bad thing is that this decay matrix, the capital gamma ij, which is also known as the Kosakowski matrix, it's in general not positive semi-definite, which means that you have some negative decay rates, which is, it's not exactly having an exponential increase of population. It's not like an anti-decay or a pumping. It's a different thing, and it's not good. And it's one of the reasons why Bloch-Redfield itself is not a Lindblad equation. Okay, so now I'm going to show you that indeed these things are not good. If I solve the dynamics with this equation for these three-level systems, so pretty simple, coupled to some bath with some spectral functions. In the upper plot, I'm showing the complex phase of the first of state one, and it should be always 0 because it should always be positive. But it turns out that it has some very non-trivial complex behavior with some oscillations, which means that the population is not just negative as it was in Bloch-Redfield, it's complex. So that's even harder to interpret as a probability and things like that. For state 2, you'll see some pretty big negative populations as well. So these things are not good. We have problems. We want to solve them. This is like the main goal of our project, to sort of fix their prescription to obtain a Lindblad master equation and try to keep it just as simple as their approach was. The first thing is to fix the non-hermiticity, and that's a very simple. We found out that with a very minimal replacement, everything was fine. Just instead of doing the geometric mean of the lambdas, which are the ones associated to the lamb shift or the energy shift, you just do an arithmetic mean, and it works very well. And this, I'm showing here a comparison, and yeah, basically it works. So great. One to go. Now the other one is a bit more involved in the explanation, but at the end of the day, you'll see that it's just as simple. So we have negative eigenvalues in this Kosakowski matrix. We want to find out first if they are relevant to the dynamics or not. So first, we're going to generate a system, calculate the Kosakowski matrix, and check its eigenvalues. This is the system, and again, a three-level system with general arbitrary couplings and interacting with an environment with some spectral functions. You don't need to care about the details too much. These are the eigenvalues of the respective Kosakowski matrices with the Bloch-Redfield equation and with the approach that these people proposed. And as you can see in the first row, the positive and the negative eigenvalues are more or less equally big, which sort of hints at the fact that the negative eigenvalues of the Bloch-Redfield equation are relevant. But if you take a look at the second one, the second row, the negative eigenvalues are about 2 orders of magnitude smaller than the positive ones. And this suggests that we can maybe get rid of them just drastically. And there are many lines here, but this shows, and the only line you need to focus on is the one with the green exclamation point sign. That's the deviation of the dynamics calculated with this master equation after removing the negative eigenvalues. And you can see that the deviation with respect to the exact dynamics is quite small. It's below 10 to the minus 2, which is basically a testament that shows that the negative eigenvalues can indeed be discarded and no big modifications to the dynamics are incurred by that. But this is, I just showed you for this for one system. I could have handpicked it so that it showed what I wanted to show, but I'm going to be thorough and show you that if we do the same for 1,000 randomly generated systems, we do the exact same thing, and we plot the negative and positive eigenvalues in this histogram. Notice that the x scale is logarithmic. Well, you see that with the Bloch-Redfield equation, the upper plot, there is a first peak that in dark blue and highlighted with this yellow rectangle. And after you do this procedure of taking the geometric mean, well, that first peak is shifted to the right about 2 orders of magnitude, so closer to 0. And this is in agreement with the previous slide, and it shows that we can basically remove them. So our prescription is very pragmatic. We take the Bloch-Redfield equation, we apply the geometric mean replacement that these guys proposed, and then realize that you can actually remove the negative eigenvalues without losing anything. And the end result is that you have a true Limblad equation that satisfies all of the mathematical assumptions of Limblad's theorem. So that has some other mathematical benefits added. And this is our main result. And with that, I'm going to switch to some conclusions. I've told you, I hope I've convinced you, or that you were already convinced that master equations are important, especially in this field of quantum everything. We saw that some previous attempts had pitfalls. Were not really as robust as you would have liked them to be. So we basically came up with a solution for one of these approaches that basically gives us an effective, relatively simple prescription to find a Limblad equation out of the Bloch-Redfield equation that's both related to the environment and has all the mathematical benefits of a Limblad equation. And with this, I'm done. So if you have any questions, I'll be happy to answer.
Thank you, Diego, for the presentation. We have time maybe for one fast question because we are a bit late on schedule.
Thank you for the talk. I wanted to ask about the nature of the bath. If you are, maybe you implicitly said it and I just didn't get it, but how important is it that you assume is Markovian or any other structure?
Okay, for their method to work, this is all weak coupling. I didn't explicitly say it. We've seen some open quantum systems that can, equations that can deal with strong coupling by importing part of the environment into the system. This is weak coupling in the sense that we're describing the atom or two-level system alone, and it's the effect of the electromagnetic modes or whatever environment that we have on it. So it has to be weak coupling, and it works as long as the Bloch-Redfield equation itself works, with the added benefits of it being a Limblad equation. So basically, you need the bath to be Markovian enough for weak coupling, and that's enough.
Okay, maybe one last question. Okay, there is.
Hello, thanks for the talk. I wanted to ask, because if I understood correctly, the whole point was that you get these negative eigenvalues which mess up your complete positivity property, and then you just remove them. My question would be then, in this initial procedure, what is your intuition about how these negative eigenvalues come to be? Because they shouldn't be there, that's the whole point.
Well, the negative eigenvalues are there from the Bloch-Redfield equation. And it's hard to say why they're there. They just are there. I guess whenever you're not doing something that's simple enough, nice mathematical properties are not necessarily a property of your equation. And so that's why they are there, so to speak, in block Redfield. What's important is that we notice that after doing this geometric mean, they become way smaller than they used to be. And it's not easy to give an intuition about why this happens, because these matrices are large, there are many decay channels, and those decay channels don't have an immediate interpretation. It's not like it's this state decaying, it's like all of these states decaying to all of these states in a coherent, well, as coherent as decay can be, way. So I don't really know how to give you more insight in that regard. But
Okay,
thanks for the question.
Okay, so let's thank Diego again. Okay, so we move on to Maxime Letnev from also the Autonomous University of Madrid. So you can start when you want.
Thank you, Carlos, for kind introduction, and thank you for having me here. Today I'm going to present my talk, which is entitled Lindblad-Meister equation capable of describing hybrid quantum systems in the ultra-strong coupling regime. Let me start by briefly introducing the motivation behind our work. Our work is rooted in the field of quantum optics, and one of the central questions of the field is how we can efficiently manipulate by properties of light or matter through their coupling. And as a prime example, you can think of spontaneous emission of an atom, which can be significantly altered in presence of the optical cavities. And obviously, if you want to achieve even more control over the properties of light or matter, you would like to get even higher coupling strengths. And that's how you come to the concept of the ultra-strong coupling regime, where your coupling constants becomes comparable with natural frequencies of the of your oscillators, which are in this sense like optical cavity resonance or electronic transitions in the molecule. So, and over the past decade, this has been these strong couplings have been achieved in different physical platforms, ranging from superconducting circuits to optomechanical systems. However, from the theoretical point of view, it still remains a challenge how we can treat dissipation in the ultra-strong coupling regime, because standard quantum optical tools are known to fail in this regime. So here in this talk, I would like to tell you the intuition behind this failure and to provide our solution to this problem. So if we want to consider absolutely general setup, we start with macroscopic quantum electrodynamics framework, which have been nicely introduced by Johannes. And so it's quite complicated. It contains a continuum of modes. The most important part here is interaction term, which contains so-called spectral density, which encapsulates all the information about electromagnetic environment. So as I told, it's quite difficult to solve, but it can be done by some advanced numerical methods. But we would like to find some more practical way. And what people usually do, they kind of implicitly decompose electromagnetic environment and take just one mode, while others can be traced out. And these traced modes form a reservoir, and all the system can be now simplified to the so-called Rabi model, where emitter interacts just with one single cavity mode, and all the losses are introduced through so-called Lindblad-Meister equation, which have been just discussed extensively by my colleague Diego, thanks to him. So, and as you can imagine, to go all the way from the original equation with continuum of modes to the simplified equation, we need to apply some approximations, and in principle, this approximation don't allow you to use this approach in ultra-strong coupling. So, if one one wants to use it, we will find some non-physical effects, and in particular, if ultra strongly coupled system is in ground state, it will tend to emit photons from this ground state, which is absolutely artificial effect which is introduced by approximations which are not valid in this case. So why does it happen? In order to answer this question, let me consider the dissipation operator of the cavity. So in the uncoupled basis, it basically drives you from the excited state to ground state. It corresponds to downward transition. However, if we go to the hybrid basis, to eigen basis, with the same operator, we will see that it will correspond to not only downward transition but also to upward transition. And basically, it means that your dissipation operator pumps your system, and this is not good. And but once you know the problem, it's already half of solution, and people came up with so-called dressed basis master equation, where they basically just remove this upward component of the dissipation operator. Like this is quite widely used in the community of ultra strongly coupled systems. However, it is not. It still contains plenty of approximations, and we are not able to use it for complex electromagnetic environment as we would like to. However, the same problem can be also understood in the formalism of spectral densities. As we know from Johannes' talk, Lindblad-Meister equation corresponds to Lorentzian spectral density, and problem is that this Lorentzian spectral density contains non-zero components even in negative part of the spectrum, while any realistic spectral density does not. The problem is that the counter-rotating terms, which are important in ultrasound coupling regime, become resonant in the negative part of the spectrum, and so like this produces artificial effects, which I have been discussing on this slide. And but how we can solve it? And basically very easily, we just remove this part. But how we can do it actually? So for this, we will use a method which have been introduced by Johannes. So its idea is basically we have a continuum of modes in the original problem, and we want to replace it by a set of few interacting lossy modes. And this model, from this model, we can take a spectral density, and basically by fitting procedure, we can get an equivalence between the original spectral density and the model spectral density, and it will give us the same dynamics for the system. Here, also importantly, I have to say that in order to reduce all the artificial effects, we have to suppress spectral density at negative frequencies in order to not have the effects which I have been discussing in the previous slide. So this is a method, and now let me discuss the results. So first, we consider interaction of a two-level system with a quite simple electromagnetic environment, which is basically just one mode coupled to ohmic bus. And we are going to use first we are going to use standard methods, which is first Lindblad-Meister equation. And as you can see, if we look at emitter population in this setup, we will see that Lindblad gives you overestimation in steady state, which is because of the effects I have been discussing before. So basically, the problem is that in the negative part of the spectrum, you still have contribution. And if we do this trick with dressed basis master equation, we see that how we can improve the situation. And indeed, we have quite good convergence with numerically exact approach. However, it's not perfect. I can say you that there are some deviations because of some inherent approximations. Now, if we apply our approach, we will see how it gives even better agreement with numerically exact method. And basically, this happens just because we fit spectral density very well in positive frequencies and also suppress it at negative frequencies. Also, as you can imagine, accuracy of our method depends a lot on where you put this threshold. If you put it here, you suppress a lot. If you put it here, you don't suppress anything and you still have the same problems. So here I render you the dependence of error of our method on the position of this threshold. And as you can see, for high enough threshold, we still have quite a huge error. However, if we decrease this threshold level, we see how our error starts to drop continuously. However, for 3 and 5 modes, we see that it starts to increase again for some values. And this happens basically because while decreasing the level of threshold, you also increase the complexity of the fitting. And for 3 and 5 modes, you're already not able to fit your spectral density and at the same time constrain it at negative frequencies. So that's why you get increase in error. However, for 10 modes, we don't have this behavior. Also, I have to say that even for 3 modes, we already can get way better agreement with numerically exact result than state-of-the-art dressed basis master equation has error at this level. So let me now go to more sophisticated structure. So we considered interaction also of a two-level system with electromagnetic environment, which you can find from this geometry, which is nanospherical dimer, like the geometry which is widely used for obtaining strong coupling with just few emitters. And first, what we do, we basically use our approach, but only over resonant frequencies. And we see that we still have the same problem. We have overestimation of our steady state because of artificial pumping problem. And if we now apply our full method over the whole frequency range, including negative frequencies, we see that how it can improve situation significantly. So I showed you these results, but one would say still that we are able to reproduce well only emitter observables, but it's actually not the case. If we would like to look at field observables, we're also able to catch them through our method. So here I show you how our approach converges with numerically exact one. If we look at the total photon number in our system, while if we don't care about spectral density at negative frequencies, we see constant pumping, which is artificial feature. So now let me go to the conclusions. In the end, what we did, we proposed a method which is able to consider dynamics of hybrid quantum systems in arbitrary coupling regime with arbitrary complex environments. Like our method provides results which are better than state-of-the-art approaches, and despite in kind of arbitrary origin of the modes involved in our model, we're still able to find results with for field observables. With that, I want to acknowledge my supervisors, Johannes Feist and FJ Garcia Vidal, and I would like to thank you for your attention. Thank you.
Thank you, Maxim, for the presentation. Maybe there is a question in the audience.
Thank you, Maxim, for the nice presentation. In your method, you have to fit the spectral density and you have to suppress the negative frequency tail. But you also speak of a window of frequencies in which you let your few modes to exist.
Mm-hmm.
How deep into the negative part do you have to get to suppress? Is it possible that you suppress from, say, 0 to -1, but then from -1 to -2 it goes up a little bit or something like that? Or how far away do you have to set the fitting window?
Okay, this is a very good question actually, and thank you, Diego, for your support. So yeah, it's right that in principle it will depend on the system where you want to suppress and on the result you want to get. But in principle, you can try to write down the how to say. You can basically define the spectral density at anti-resonant frequency. So basically, like symmetric to here. Like you can get the spectral density here and compare it with the frequency. And if it's small enough, you're fine. It's in principle it's analogical to this ultra strong coupling condition when you have to compare coupling strengths and natural frequency.
Okay, so let's thank Maxime again. And now we can head to the last talk of the session. Okay, so the last talk is by Laura Castellano from the Universidad Complutense de Madrid. So whenever you want.
Okay, so thank you everyone for being here. I will really try to be brief, but this is the work that I've been recently doing with my supervisor, my PhD supervisor, Angelo. So let's begin. So this work started as a natural question that rose up after 2015 work by Cuiz Pérez Garcia and Michael Wolf, in which they asked the following question. So they had this setting about a Hamiltonian that had local on-site interactions and nearest neighbor interactions between pair of particles. And this was a lattice Hamiltonian arranged in a 2D lattice of size n. So the Hamiltonian also had the properties of being finite d-dimensional, like the local Hilbert space was finite, and this will be relevant later, and also was translationally invariant. Okay, but then they ask, okay, so given this local description of our Hamiltonian, can we actually know if the limit system, like in the thermodynamic limit, is going to be gapped or is it going to be gapless? And they show that no, the problem is undecidable. But then we ask, okay, but Hamiltonians in nature, they have some kind of symmetries. Usually, it's very natural for them to have that. So maybe the symmetric Hamiltonians can form a problem, a subset where the problem is actually decidable, and you can actually see if the problem is gap or gapless. However, as the title of the talk says, no, we unfortunately we managed to see that the problem is still undecidable, even if we have some certain symmetries that are rotationally invariant supplies to the lattice. Okay, but what we have to change, what we lose, is the local interaction is now a 4-particle interaction instead of 2. Okay, but the dimension is still finite. That's the point. Okay, so well, the problem is still undecidable. That's what it is. But I'm going to show you a bit about how this construction done. Okay. So first of all, for those of you who are not familiar with the term undecidable and how this works, this is a very it's very studied property in computer science, okay? And an undecidable problem is just a decision problem, so one whose algorithm output only yes or no, binary problem, but no algorithm exists that can answer correctly on all inputs of this problem, okay? But this doesn't mean that maybe in some particular inputs you can actually see and have an answer yes or no. But the point is that if you want a general algorithm to solve every possible case, you won't have it. And this is what undecidable means. Okay. And the most famous undecidable problem is the halting problem that was due to Turing in 1936. And a very, very useful tool in computer science is to reduce your problem that you suspect to be undecidable to this halting problem. That actually the proof of the halting problem is quite simple. As you can see, look it up on Wikipedia, I think. But the halting problem just asks, okay, I have this program on this input. Will it hold? Yes or no? That's the whole problem. But despite being so simple, there exists no general algorithm that is going to solve this problem for all possible input pairs. Okay. So this is what we're going to do. We're going to encode this halting problem in our Hamiltonian. And you may ask, like, okay, but how do we do that? And in order to do that, we need to represent any possible computation and any possible input, because we're talking about the halting problem. Okay. What we're going to work is with an universal Turing machine that is basically a mathematical model that can simulate any algorithm. Okay, you can treat it by now like a black box, but the point is that it can simulate any algorithm because it has an infinite memory, an infinite tape. Okay, so every computer you see, it's a particular instance of a Turing machine, but of course your computers don't have infinite memory, and that's the power of the mathematical construct. And then to represent any possible input, we of course can do that with a normal Turing machine. But the point is that if we want the local Hilbert dimension to be kept finite, we need to go to quantum, and we do a quantum phase estimation algorithm that is going to write deterministically this input for the universal Turing machine. Okay, so now we have finally a quantum Turing machine that is just dovetailing the two machines, the universal Turing machine and the one that writes the input that we desire to feed this universal machine. And then with this quantum Turing machine, what we do, and that was done also in the previous work, and it's based on all the previous work on 2009 by Gottesman and Irani, is that we're going to encode this quantum Turing machine evolution in a one-dimensional Hamiltonian on a chain, basically. So what they show, Gottesman and Irani, is they do it for another purpose, okay? But the point is that you can encode this quantum Turing machine evolution in the ground state of a desired Hamiltonian, such that the ground state is going to be the superposition of all possible computational history states. So you initialize your chain, and the point is that you're going to give energy to any state that is illegal, and being illegal means that it doesn't follow the correct evolution of the computation. Okay, so it's the superposition of the computation on the state 0, 1, 2, 3, etc. Okay, and this is done by giving a really explicit description of all these local interactions and defining all the regular expression and using all transition rules, illegal pairs. Yeah, so you have an energy penalty for everything that is not valid. So therefore, you guarantee that in the ground state, you're going to have the correct evolution. What we need to add is we need to grow the local dimension actually a bit, because we want to allow for the computation that can be seen as a particle moving from left to right of the chain, but we also want the particle to be able to move, to initialize on the right and move to right to left. Okay, and then producing two possible orientations for this computation, and then two possible ground state. But however, we're going to, this is a trick that we'll use later. But then the halting problem enters here, and what we're going to do is, okay, we have this evolution on the chain, and if everything is correct, we're not giving any penalty. Okay, so ground state energy is 0. But however, if the machine eventually halts, we're going to give a small energy penalty. It has to be exponentially small, as you can see. L is the size of the chain. Okay, but this has to be so small because we don't want it to be confused as an illegal state, because it's actually legal, it's a valid evolution, but it just halted. Okay, but as it is exponentially small, we're going to amplify the energy difference and then actually go to the limit. Okay, and for amplifying this, what we're going to use is Robinson's aperiodic tiling. That is basically we just add another layer, another Hamiltonian, which is a tiling Hamiltonian. You have a finite set of tiles, which are these Robinson tiles, and then if you correctly arrange these tiles, you will end with a picture like the one we see here, which is basically infinitely many squares of sizes 4 to the n for every n. Okay, so you can see here like the small squares, then bigger ones enclosing 4 of them, and so on. And this picture, of course, grows up with in the whole plane. And then what we're going to do is we're going to put our chain Hamiltonian on top of every edge of these red squares. And therefore, when we sum the whole Hamiltonian up and go to the limit, what we're going to have is, in the halting case, the energy is going to diverge to infinity, because we also do a corresponding energy shift. Okay, I know it was 0 previously, but we do an energy shift. And then the energy is going to diverge to 0 if the machine halted. But in the non-halting case, the energy is going to go to minus infinity. Okay, so we have two totally polar opposites. And then we also wanted these two possible orientations because in order to have a unique ground state, we're going to add some terms on the corners of the squares to force a clockwise orientation. So the computation can be read as going from left to right, top to bottom, then right to left, and then bottom to top. Okay, and this is a unique ground state that is going to cover all squares on the plane, and it's invariant under rotation because if we rotate our lattice, everything stays the same. And the tiling is the same as the previous construction that also used this Robinson tiling, but we needed to change the Hamiltonian because now the particles are on the edge of a tile. If we think of a tile, now our particles are, so a tile has 4 different particles, each of one on the edge. And previously that we had, if it was just a particle was described by a tile. Okay, and that's why we have the local interactions described by 4 interactions. Okay, and this is because of we needed to actually guarantee the symmetry of the all of the layers that this construction has. So finally, what we're going to end with is with this H Hamiltonian that is going to have a minus negative energy if we go to if it didn't hold, but it's going to have a positive energy if it halted. So we're going to fuse it with a dense spectrum and a trivial spectrum Hamiltonian with a corresponding shift in the dense spectrum to make it match with the lowest energy level. So in the end, we're going to end with 2 different possibilities. That is that the actual final fusion Hamiltonian is gapless if the machine did not hold. But however, if the machine did hold, then the final Hamiltonian is gap, as we can see in this picture. So this was very quick, but this was everything I wanted to talk about. And hopefully, I really, really want this to be in archive soon because I'm tired of writing now. But yeah, so that's all. Thank you very much for your attention.
Thank you very much, Laura, for the interesting presentation. We have one question here.
Thanks a lot. So, if I just want to make sure I understood correctly, your point is since you were able to map it to the halting problem, you can now claim that it's undecidable, or
yes, because you encode. What we do is we construct a family of Hamiltonians. In what that we can see that the problem of seeing if it's gap of gapless, it's going to depend on the halting problem. So therefore, yes, the problem is also undecidable.
Okay, any other question?
Hi, thanks for the talk. I'm curious about the physical implications of this because it's something very mathematical. So that
Yes.
something is indecidable, that depends on mathematics axioms and all that stuff. Is there a possibility that this kind of Hamiltonian could be engineered, quantum simulated,
Yeah.
and then suddenly you have an experiment and you can say,
Okay.
well, the answer is yes or no?
Yeah, I see your point. I actually get this question a lot because you can imagine I'm not a physicist, but so yeah, our point was to tackle this problem of of trying to give it symmetry to the Hamiltonian, so it can be like more natural in a sense, right? Can it be engineered? So I don't know if the tricks that you need to do to actually fabricate a Hamiltonian in a lab. So I don't know if you can actually find this kind of construction like directly on the lab. But what we try to do is like go the other way and say like, okay, but can this kind of Hamiltonians like just exist? Like, I don't know if you have found them or not, but the point is that they can exist. So yeah, I don't know if you can actually engineer this in a lab, if that's your question.
But in that case, imagine that we can, in the case we could perform this in a lab, and we can then see if it's gapped or gapless.
No, the point is that you're not going to, I mean, maybe you can try to construct the Hamiltonian and actually construct this construction in a lab. But the point is that even if you construct it, you have no way of guaranteeing if the system is going to be gap or gapless in infinity.
But you can get an answer.
Sorry?
From a physical point of view, if you perform the experiment, can you measure if there's a gap or not? Or am I missing something?
Maybe you can get it for a particular system. The point is that the undecidable property says that in general, for every possible Hamiltonian, you are not going to be able to do that. maybe you can actually find a Hamiltonian with all these kind of symmetries and everything that you can perform an experiment and see something. But the point is that maybe your particular Hamiltonians have some other special properties. So you have to think of the Hamiltonian family as some different kind of subsets, that each one is going to be different.
Okay, it has to be fast, okay?
Regarding your answer to this last question, in which you were saying, okay, in general, this is going to be undecidable, but maybe you can find one that you can see something. Then my question would be, okay, would one be able to restrict this family of Hamiltonians further down so that one can indeed know if for this more specific, more special family of Hamiltonians, the problem is undecidable or not?
Yes, definitely. That's an interesting question. And that's what we actually tried to do, because the previous work was Hamiltonians in general undecidable. We said, okay, but what about the symmetric ones? In general, this is not such a specific subset. So this problem is still undecidable, but maybe then you can go further down and find some other classifications and decide.
Okay, thank you.
Okay, so with this, let's thank Laura again. This was the last talk of the session, but Guillermo wanted to tell us something.
Yeah, just a quick comment. Is there anyone who has not put the poster? Everyone has placed it? You have not? Okay, look for me at the following break at 4 p.m., right? And we fix that, okay, because there is some mess with the numbers. And also, as yesterday, there are two cafeterias, one a bit farther and one really close here. You can go to any. Enjoy your meal.